Good afternoon, everyone. Welcome to the second webinar series on this data-driven modeling. So today, we're going to talk about how to do data-driven modeling of self-organization from observation data. Okay. So here's a brief outline of this webinar. We will introduce briefly what a self-organization is and what does it mean, and how can we actually understand it from the dynamical system point of view. And then we will go through briefly about how to do forward modeling for self-organized dynamics. And then from that, we raise the questions whether we can actually learn the dynamical structure from observation data so that we can do data-driven modeling of self-organization. And then after that, we'll discuss some extension on how to extend this current learning approach to more complicated dynamical systems and actual real data. And then we'll have a brief code demonstration towards the end, and then we will conclude the webinar series. Okay. So yeah, so self-organization happens naturally in the nature and provides a lot of interesting patterns we can see. For example, these static stripes patterns on zebra, so really interesting. And besides being static, you can also have the self-organization patterns appearing from a dynamical patterns. So for example, this swarming or flocking of starling taken on YouTube. You can also have these flocking or swarming form into a spherical shape. So for example, this spherical shape formed by milling of fishes is interesting pattern. Okay. Besides these patterns forming in the spatial spaces, you can also have patterns forming in phase spaces. For example, this synchronization of this frequency of clocks. Okay, you can actually happen in phase space. Okay, all of these can be explained by a term called self-organization, which means that you have some kind of global order or global behavior emerging from initially chaotic states. And you can actually achieve this emergent behavior using only local interactions. So three different layers of meanings. So initially disorder states, and then at the end you emerge a global order, and you have this global order emerging only using local interactions. Okay, and self-organization as of itself is a really complicated subject. It encompasses many different areas of research. And today we'll just focus on the collective behavior point of view and also some pattern formation due to this self-organization. And then we want to understand that from the dynamical system point of view, and then using machine learning to actually provide these dynamical systems. Okay, as you can see, self-organization happens in many physical, chemical, or even biological systems. So in physics, you can have superconductivity, spontaneous magnetization, crystal growth happening due to self-organization. In chemistry, you have the molecular self-assembly or self-assembled monolayers. That's due to also self-organization. Okay, we have already seen some of these flocking of birds, milling of fishes happening due to self-organization. You can also have these social behavior in insects. For example, ant raiding is also considered part of the self-organized behavior. Okay, for human, because human as intelligent animals also have this so-called group behavior, herd behavior that you can actually see happening for us. Basically, just like, for example, following the group. And you can also have this happening, the abstract concept. You can also have it happening, self-organization happening in market economy and traffic flow. Okay. And if we can understand these self-organized behavior, we can actually use it to actually analyze a lot of different objects. For example, we can actually analyze opinions to study how consensus is actually formed and other social behavior of humans. Okay, and if we know how animals interact with each other, we can actually study animal migration. And once we know how they migrate, we can actually do incorporate appropriate conservation policy for these animals. Okay, and you can actually have abstract concepts For example, self-organization can be used for finding global minimizers. You can actually apply the so-called particle swarm optimization to find global minimizer in optimization or in unsupervised machine learning. Okay, and once you know how actual animals, agents, intelligent agents interact with each other, you can actually build that in robots, into control, and then you have these so-called digital twins that can actually interact or move according to almost biotic interactions between the robots or UAVs. Okay, so well, before we actually go into the details on how to understand that from the mathematical point of view, the idea that a dynamical system can actually lead to increase in order. So actually a little bit counterintuitive to those who know that the second law of thermodynamics, that the things actually increase in chaotic behavior, but self-organization actually is an increase in order. This idea that dynamical system can lead to increase in order actually happens a long time ago. In ancient Greeks, some of the philosophers already argue that given enough time, resources, and even space, order would naturally emerge by itself. Okay, and then in this 1637 book, the self-organization as an idea first appeared, and they actually use the term self-organizing in the 1790 books. But before all of these, mainly people just talk about self-organization as a philosophical concept. It's just that through observations, you can see that happening in the natural world, that some kind of global order would always appear, but the people don't understand that from the mathematical point of view, and they try to explain that. Okay, and then in this 1947 paper, William Ashby actually we introduced the self-organization, the idea, and also introduce the dynamical system that actually give you the self-organizing behavior. Okay, and then from that time on, this idea caught on, and then it becomes really popular research item. In fact, in 1960s, there's a huge first of its kind conference on the principle of self-organization happening at University of Illinois, and then Norbert Wiener actually took this idea and produced his synchronization models. And in his book, in his 1961 books, he actually talked about in details how self-organization actually happening in communication of neurons and cells and all of this stuff that actually gives up the synchronization in cells. Okay, so now we know that we can actually explain self-organization using dynamical system. Okay, basically we allow this system of our interacting agents to interact with each other. So it's only pairwise, so local, hence the word local, pairwise interactions. You can have these agents of different types. You can even have these agents interacting with the environment. Okay, as long as you have pairwise locally interacting agents, then the whole thing as a system will emerge some kind of global behavior. Okay, but the only thing left is how can we define what do I mean by interactions or influencing? How will agents influence each other? So I want to give you an example of how to model flocking of birds. So the famous flocking model would be in this 1987 paper when Craig Reynolds first introduced this flocking model and proposed this idea of 3 different flocking zones. So it's actually really, really natural. So when agents get close, they should repulse. So we have this repulsion zone. And then when agents get far away, they should attract each other so that the whole system will stay in a group. So we have this attraction zone. And in the middle of it, you should have the agents trying to align their headings so that they will try to fly in the same direction. So that's the basic flocking behavior for this flocking model. Okay. And then people use this flocking model to propose many different kinds of self-organized dynamics. But what we want to do is, can I actually look up the position of these birds or these agents and then produce a dynamical system to actually explain the future behavior, to predict the future behavior of these agents, and at the end actually capture the essence of self-organizing dynamics. Okay, so for example, if the agents are about to flock and I observe them way before they flock, can I actually produce a dynamical system to predict that this group of agents will be flocking together? That's what I want to do. Okay, so the next thing is let's look at some forward modeling of self-organization. Okay, so let's look at some really basic examples. First is this first order example of n agents. Okay, we're going to assign each agent with a so-called state vector that contains either its position, velocity, emotion, etc., or everything, anything about these agents. And I want these agents, the change of this state of this agent is an average sum of all of these functions, which we call it the interaction law. So govern how the agents of I prime interact with agent I. Okay, so it's an average sum of all these interaction law applied to these pairwise distance and then weighted by this pairwise difference. Okay, so I want this change to follow that. Okay, once I have that, then I know that if I put a certain properties of this interaction law or interaction functions, then I can induce a certain kind of self-organizing patterns. For example, clustering, if I have all the fees being positive, or synchronization when all the faces would swing or text together. So all of these different stuff, if I put a certain properties of this C. So for example, if I have this interaction kernel or law, a function that governs how agents interact with each other, being this compactly supported function. So it's all positive from 0 to 1. Then after 1, everything is 0, and it's also discontinuous. So from 0 to about 1 over to 1 over square root of 2 is 1, and then from 1 over square root of 2 to 1 is 0.1. So it's actually that means that when agents are closer, you feel stronger interactions from the other agents. When agents are far away, you feel weaker interaction from the agents. So makes sense in some cases. Okay, so if I have this kind of positive, even complex supported positive interaction kernel, then I can actually induce clustering because you only attract each other. So basically, when they're close, you would actually flock or move together. So at the end, you will actually converge to certain clusters. Okay, so here I only had the dynamics run up to time 20. If I have it run way beyond 20, then the trajectory will eventually converge to about 1, 2, 3, probably only a few clusters. So this is a simulation of 100 agents. So at the end, you only have about 4 or 5 clusters of these agents together. Okay, so this is actually this model using a positive fee, even though it's complex supported, so it's local interaction. So again, so it's complex supported, it's local, and then you can still have a global behavior of the whole system. Okay, and in this case, it's a cluster. So everything would just join together, will form a few group of agents, way less than the initial number of agents. Okay. So that's the first example, really basic forward modeling of a first order system. Okay, then we can also talk about a second order dynamics where you have now this time we're going to think of that the state vector xi is only the position vector. Okay, and then the second time derivative in this case, because xi is a position, so the second time derivative becomes the acceleration. So the acceleration is some kind of external forcing plus still an average sum. So it's over the whole system. So the n here is the whole system of a energy-based, which is explained why it's phi with the superscript e there. So it's energy-based interaction kernel. Okay, and then weighted by the pairwise difference plus an alignment-based interaction law. Weighted by the pairwise difference in velocity. So it's like the pairwise headings. Okay. So in this case, we're going to assume that phi is actually induced by some kind of energy functional to provide the so-called close range repulsion and then long range attraction. Okay. And then phi A here provides the alignment interaction law. That means it's in the middle of it, you would just align the pairwise headings. In this case, given by this formula, is actually changing only the pairwise heading here because it's the difference between each velocity. Okay, so you can see this function, and then we're going to assume that the system also experiencing some kind of external forcing from the environment. So you can think of this capital F here as some kind of friction with the environment or some kind of radical quotient with some kind of fluid flow. Okay. So if I also put on a certain properties of these interaction kernels, in this case should be both phi E and phi A, then I have another different set of self-organized dynamics, emergent behavior. In this case, I can have flocking if I only have the alignment interaction there. I can even have mulling. That would be the balance between the alignment and all those, also the external forcing. And then with swarming would be more complicated. You probably have all three of them present in the dynamics. So let's see an example. In this case, we're going to assume we're going to play with the famous Coker-Smell dynamics when we have a simple alignment model. So in this case, there was no energy-based interaction law, only have alignment-based interaction law. That means that my interaction law is only going to align the pairwise headings. So the birds are only going to align their velocities. So if I have that, even though this interaction kernel is actually a global, but it decays really fast towards infinity. So you can also think of this probably practically local. This is actually an exponential decay. Okay, so then we will have that the group of birds will actually at the end flock together. That means that they will fly at the same velocity at a appropriate amount of time within this dynamics. So yeah, so as you can see, the trajectory shows that initially the position and velocity of these birds is chaotic. You can see that from this initial time here. So this trajectory, another thing is this, now we have a 2D trajectory, so we need to use the color scheme to indicate the flow of time. So the time flow from dark blue to light green. So in that case, this is where the agents are, okay? And then they will fly all the way to the end, and they will fly with, all of them will fly with the same speed, with a almost locally interacting kernels, and is only align their headings, so they do not provide the repulsion. So this Coker-Smell model will actually allow the birds to collide into each other. Just that at the end, they will have the same velocity, okay? So then you would want to say, well, what if I want to build in this collision avoidance into this model? Then you want to build in this external forcing based on energy potential. So in this case, we have this another flocking model where we have flocking with the external potential. That means that the energy-based interaction law is present. It provides this short-range repulsion and long-range attractions of these rather than the alignment base when you have only alignment in the mid-range. Okay, so in this case, I actually have a constant function for the energy-based interaction law. Is positive, so it's only attracting everything, and is about 0.1, so it's actually really small attraction. But as you can see, so because I have these attractions, so at the end, this flocking, this you can think of this area of flocking here. This whole flocking area would actually shrink because I have attractions. If I build in attraction and repulsion there, then this area will actually probably enlarge due to the strength. So in this case, I have a positive attraction forces. Okay, my alignment force is still the same as in the Coker-Smell case. Okay, and then as you can see initially, again, this is a 2D trajectory. So the color scheme indicates the flow of time. The time flow from dark blue to light green. So as you can see, initially they are chaotically placed, disorderly placed with a randomly chosen velocity, but eventually they will fly with the same velocity, and also this area when they actually flock together will be smaller due to the presence of attractive forces of this flocking of this external potential. Okay, so now we know that I have shown you two basic examples of forward modeling using the first order models and also the second order models to actually reproduce these self-organized dynamics. Okay, but then it boils down to whether you have the proper knowledge on how to design the interaction laws so that you have these self-organized behaviors. Okay, what if we have only the observation data? Can I actually do that? Derive a dynamical system that actually explain this data and also give me the corresponding self-organized behavior. Okay, so go back to those questions. Can I actually learn the interaction law from observation data? And I want this final models that actually has some kind of physical meaning. I don't want it to be just a linear combination of random bases. Okay, and I want my method to be also effective. That means that I can apply to both first order and also second order models. And also later on, I can extend that from homogeneous agents to heterogeneous agents. And I also want it to be efficient. That means that I want my learning method to be applicable to a set of big data. So big data set, I can still do it in roughly linear in terms of the number of samples. Okay, so now let's go back to our simple models, the first order models again. So we're going to assume that we have a system of n agents again, and each agent is assigned a state. Remember, we assume that the state can be position, velocity, emotion, etc., everything else, or everything altogether. Just any state you want to throw at the agents, and you want these agents to have that kind of property. And again, we want, so this is more abstract. We want that the change of this state to actually decrease certain system energy. The system energy depends on the whole system of states for every agents. Okay, so it's actually a gradient flow problem, but it will be really complicated if we allow this system energy to be as general as enough. But we don't want to do that. We want to put on a certain restriction on this system energy. We're going to assume that the system energy actually is a sum of pairwise potential. Okay, so this pairwise potential also depends on pairwise distance. So we basically building this permutation invariant, also radial-based interactions into the system. Okay, so I want the system energy to be like that. Okay, and simplifying, I get back my first order model. So the change of my state for each agent is an average sum of an interaction kernel or law based on pairwise distance and weighted by pairwise differences. Okay, again, we're going to say that the phi there is my interaction law that governs how agent I prime interact with agent I or influence agent I. Okay, and then because everything is living in a Euclidean space, we're going to assume everything is just using a Euclidean norm. Okay, you can actually use other LP norm. It doesn't really matter here. So again, I already show you if I have a known properties to put on this phi, I can induce certain emergent behavior, clustering, flocking, mulling, etc. Okay. For example, this pairwise complex supported piecewise constant function. So it's when you're closer, you get 1. When you're farther away, you get 0.1. When you're too far, you get no interaction at all. It actually induces some kind of clustering. Okay. And then if I change the law to a power law, it actually induces a ring-like patterns. Then the agents will eventually get pushed out and then stay on a ring around the origin, or around the center of mass origin, not the random origin. Okay, so I have the ring-like pattern if I have power law like structure for this interaction kernel. If I put a hypertension law structure on this interaction kernel, I actually have these agents at the end placed out on a soccer ball like patterns. Okay, so different interaction kernels will give a different self-organizing behaviors. What we want to do is when I observe this system just a little bit, just a really short period of time, and I want to learn the interaction law that explains the whole system. Okay, so in this case, I'm going to assume that I know everything about my observation data. I know that the observation data corresponding to which agent, so I can actually number my agents. I know the position. I know the state, and also the duality of the state is the state can be more than just position. So yeah, and I have all the agent information. Okay, I know this I represent to which agent. The only thing that is unknown here is the interaction law, which governs how the agent I prime interact with agent I. Okay, that's the only unknown. Okay, and now I want to learn. Okay, So before I do that, let's just put on a certain assumption on this interaction law, assuming that I have really nice function to deal with. Okay, basically this is like a bounded first derivative. Okay, and I also want to use a vectorized notation. I'm going to put everything into a huge vector. So all of the states for the whole system, I'm going to put it into this big capital S here. And then all of the right-hand side with all of these average sum of interaction laws, I'm going to put it into this capital FE. So FE depend on the interaction law and also the position and of this system. Okay, by writing that, I'm actually rewriting the system of ODEs into one big equations that the x dot is just FE, which is a huge right-hand side, depends on x. Okay, so in this case, and we know that my problem setting is I'm given the x and x dot, and I want to learn the function that explain the relation between the x and x dot. Okay, so basically the problem, I can rewrite the problem and restate it as, given the observation of big S and big S dot, can I actually find a right-hand side function to explain the relationship between the two? Okay, it looks awfully similar to a regression problem. However, the regression approach is not applicable here because we do not have data independence. Okay, because I have time series data, so I cannot just simply apply a regression to that. Even if I want to do that, okay, I want to learn the right-hand side directly. Okay, then I will still run into the trouble because the dimension of my observation data is so large. Okay, if I even assume a certain kind of sparsity onto this right-hand side, I will still run into problem. Okay, because that my right-hand side has a special structure. Well, remember, the right-hand side actually is independent of the permutation. If I permute this position of these agents, I still get back the same right-hand side. So I need to build that in. And also my right-hand side function is radially based. It doesn't care about the actual directions. So if I build these two in, it will be a huge loss function even for deep neural network to train. Okay. So we need to reconsider the special structure of this right-hand side. Remember, we defined this right-hand side as an average sum. So it's a sum of an interaction kernel. A law depends on pairwise distance. Okay, we need to emphasize this point that we're actually basically, although the observation data is of high dimensional, but the structure of this function, the only unknown, is only one dimension. It's just that all of this data is hidden inside this sum instead of given to you directly. So we need to be careful about that. Okay. So yeah, let's go through the learning framework. So this time I'm going to assume everything is going to be discrete. So I have a discretized time instead of a continuous time. And also I'm going to assume that my trajectories can be generated from a black box, so that is actually generated corresponding to certain initial states. I will have different initial states for my trajectories observations. Okay, and then I'm going to construct a error functional, a loss functional that trying to minimize the true derivative of my observation data to the predicted derivative, which is based on this test function var phi here. So I shouldn't have a C here, but yeah, that actually predicted on the states, the observed states of my system. Okay, and then I'm gonna minimize this distance as small as possible at any time. So I have the observation time here and for any initial conditions. Okay, and then I'm gonna search for my minimizer over really nice compact and convex search space. Okay. And then I can obtain a unique minimizer because this objective function is convex and the search space also convex. Everything is nice. I will have a minimizer, but will this phi hat LM, which is the minimizer based on this form, converge to the unknown interaction kernel? That's my questions. Okay, so we need to understand that. Well, to prove it directly is just basically impossible. So we need to take a detour, actually introducing a middle guy. Basically, I'm just take the expectation of my discretized error functional. I'm gonna just let M, which is the number of initial conditions, go to infinity. If I do that, I obtain a expectation. So I obtain expectation of this error functional, which is calculated at different times instead of different times and different initial conditions. And I want this expected version to find a minimizer so that this expected version of my error functional is as small as possible. And then I call this minimizer to be phi hat L infinity. So I can see that the M here is the discretized in terms of initial conditions, and infinity is expected. Okay, so it's actually really easy to show that the phi hat LM is going to phi hat L infinity using just law of large number and other concentration theorem. You can actually show that. The only thing left is, can I actually show that phi hat L infinity is indeed my unknown interaction kernel, or somehow close to it, so that I can have an error band. Okay, so to show that, I need another condition, basically just bounding the expected error function that I'm trying to minimize by the distance between the test function to the unknown function. Okay, so basically the so-called causivity condition just gives me that. So that means that when I try to minimize the expected error functional, I'm also minimizing the distance between the test function to the error function, to the unknown interaction kernel. Okay, you can also think of these conditions actually really similar to the Lasse-Milgren type of conditions for finite element. So it's actually really similar to that. Okay, and with this condition building assumption made, we can actually show that with an increasingly large search space, and this dimension increase at the rate really special, actually is m to the 1/3. We get that because using just the bias invariance trade-off. So we have that. So this is the optimal increasing rate. Okay, so if my search space increased at a rate like that, then I have a learning rate, my phi hat LM, which is a discretized minimizer, okay, will converge to the true unknown interaction kernel at a rate of m to negative 1/3. Okay, so it's not yet at the Monte Carlo rate because we cannot get that. We do not have those in data. We have dynamical data, but we still have m to negative 1/3. Okay, so it's actually really good rate. Okay, and we also can have that the predicted trajectories. So phi x hat here is the trajectories produced by phi hat. So we use the estimator to reproduce dynamical data. Then we will have the learned dynamics also converge to the observed dynamics with the same time interval as m going to infinity. M here is the number of initial conditions. Okay, so our learning rate depends on m. The capital M here is the number of initial conditions. It's actually really similar to the 1D regression rate. Okay, but our problem is not cast in the 1D regression problem setting. It's cast in the inverse problem setting. We actually need to use all of this to prove the convergence. And I want to also mention that our learning rate is independent of the dimension of the observation data, which is capital D. That's because all of the observation data is capital X. So that dimension is really large. However, our learning rate does not deteriorate when you fit it with a larger observation data, either increase its number of agents or increase it in the length of each state vector. Okay, in either case, our learning rate will not deteriorate. We will maintain the same learning rate. So our learning problem is actually can actually tackle the cursive dimensionality from the point of view that the dimension of the observation data is large. Okay. However, our learning rate does not have a dependence on L, which is the number of time instances we make observations. So that is still remains open. So we're still trying to incorporate that into our learning rate. Okay. So now we have a theorem guarantees the convergence. We also have a theorem to guarantees some kind of solvability of our learning problem. The next thing is, can I actually build a software to actually learn all of this in a dynamical system? So let's go through the details on how to actually implement this learning algorithm. So we're going to assume we have discretized observation data and the derivative of this observation data. We're going to find the so-called maximum and minimum interaction radius. Just basically go through each pair of agents and find the pairwise distance data. Okay, and then out of this pairwise this learning interval is based on the maximum minimum interaction radius radii. Okay, we build a basis function. We build our search space. using either Clan B-spline or piecewise polynomials, or even Fourier basis if you know that your final solutions have some kind of periodicity in there. Okay, and then we will build that upon a uniform partition of this learning interval of this minimum radius to the maximum radius. Okay, and then we construct two matrices, one matrix and a vector. The matrix contains all the inner product between the test function, basis function added on the observation data, and the vector is the observation function added on the observation data with, oh, that should be a dot there, with the derivative. Okay, so if I write everything like that and express my test function as a linear combination of this basis, then the minimization problem becomes just a linear algebra problem. It becomes a linear system to solve. And the previous theorem that I showed you, the convergence theorem, guaranteed that this linear system has a really nice conditional number. It's well conditioned. It actually can be solved really nice. And once we obtain all the solutions, we can assemble the estimators. And then once we have the estimator, we can actually use it to predict the large time behavior of the dynamics, including whether it will flock or cluster or something like that, or other predictions that you desire with this phi hat. Okay. And another thing I want to point out is the derivatives, the derivative of these states of each agent. We can actually skip that as long as you observe as closer enough. We actually have a RKHL statement showing that the error from approximating the derivative will not affect the learning rate that much. Okay, so we can actually approximate the derivative. We can still learn pretty good with this approach. So let me show an example that this is the opinion dynamics that I just showed before, but now we have a comparison. So on the left are the true dynamics, on the right are the approximated dynamic using the estimator that we learned from the data. The center line dashed line here is the learning time. So we only learn from 0 to 10. Okay, and after that, everything is a prediction, okay, for the estimated dynamics. Okay, and then if they're on the dynamics, if they're on the same row, they share the same initial conditions. On the left are the true dynamics, on the right are the predicted. And then another thing is the reason why we want to put the learning framework using that kind of model is because once we learn phi, the interaction law, which is independent of the number of agents, independent of the dimension of the system, you can use it for transfer learning. So if I learn the interaction law, then from a system of 20 agents, I can actually transfer learn to 40 agents right away, which is why I show you here. Okay, so I only learn it from 20 agents, but I transfer learn to 40 agents right away, because I learned phi, which is independent of the number of agents. And I can actually provide you the number. This is at least a 2-digit relative accuracy in predicting the trajectories in both the normal case and the transfer learning case. Okay, so here's a comparison between the learned interaction kernel to the true interaction kernel. So the true interaction kernel is shown in black solid line. Okay, so again, it's complex supported and also discontinuous at some points, but we do not know that from the data. We only priorly, we only know that learning from the data. Okay, it's also complex supported, but because we learn it from the data, so the data says that the whole thing should be from 0 to 10, almost 10. So we actually construct the whole function on 0 to 10, but the whole thing only has effect up to about 1 there. Okay. So the blue dashed line is the phi hat, which is the learn estimator. As you can see, we can approximate the original function really well, even at some close to discontinuity points. Okay, and in the background is the distribution of the pairwise data that we actually use to learn these interaction laws. Okay, so that's the comparison. Okay, so here's the example showing the flocking models. When every bird would just fly in the same directions. Okay, so again, we have learned from only 20 agents, but we can transfer learn to 40 agents right away because we learned the phi, the interaction law, not just the right-hand side of the whole system, it's the interaction law. Okay, so Ibonon, they don't show any differences. In fact, if they flock, they flock. So actually, we actually preserve the flocking behavior in that sense. And here's a comparison between the alignment-based. So we have the Cocker-Smell model. So we only have alignment-based interaction law. Okay, so in showing the background again is the distribution of the pairwise data. Okay, and then blue dashed line is the alignment-based interaction kernel, and the black solid line is the true interaction kernel. So we can actually follow that really close, especially towards the end. And then the alignment, this is the pairwise heading data, because remember the alignment is actually the data, the dynamical data from the Cocker-Smell flocking dynamics. The data is actually aligned by pairwise heading. So we actually, this actually learned together from the observation data. So we actually have both. Okay, and then as you can see, that's the flocking model. And now we have the flocking with external potential. That means that we have an energy potential to actually control the size of this group of flocking. As you can see, eyeball norms, this three sets of trajectories, they have no differences. In fact, when we transfer learn, they even share pretty close semblance to each other. And then we can actually learn the energy-based interaction kernel. I want to point out that although it looks really hugely different, but if you look at the scale, so here is only 0.1, and it only goes up to 1.01. Okay, so it's relatively about 2 digits relative accuracy that we learn from this. Okay, we just zoom in so that it seems that they are hugely different, but if you zoom out, the two lines actually match up pretty close. Okay, and this is the alignment-based interaction kernel that we learn from this data, from this flocking with external potential data. Okay, so now we have discussed in details how to build up the learning framework to learn a first-order model. Okay, so now we're ready to extend that to more complicated cases. So for example, let's recall the first-order model that we use for build up our learning algorithm. Okay, remember that the change of each state is an average sum of the interaction kernel, depends on pairwise distance and weighted by pairwise differences. Okay, now this model is only applicable to a system of homogeneous agents. That means that the agents are of the same type. Okay, but in reality, in actual applications, agents don't necessarily belong to the same type. We can assume that agents belong to different types. Okay, we're going to assume that we can actually divide these group of agents into several different types, and each set of different types they don't intersect. So we don't have agent belonging to the two different types. It's just one agent to one type. Okay. And then we'll just extend this model here from only depending on each pairwise distance to also depending on the types. Okay, so that means that phi ki k prime means that this interaction is from the agents xi in the ki prime interacting on the agents xi on the ki. Okay. So if you have capital K types of agents, you have a total of K squared different interaction kernels. Okay, and then n sub Ki prime here is just the number of agents in that certain type where I prime belongs to. Okay, and then you would think, well, once we build everything into a tight dependence into this interaction law, how will you actually learn that? As it turned out, the learning algorithm is actually roughly exactly the same as once we change the S norm, which is how we measure the huge state vector into respecting the number of different types. Once we do that, then we can learn right away. Okay. So here's an example showing how to learn on an observation of a predator-prey dynamics where you have a single predator chasing a group of prey. So in this example, we have a 10 agents, total 10 agents. So it's one predator versus 9 prey. Okay, so we again on the left are the true dynamics, on the right are the learned dynamics, and if they are on the same row, they share the same initial conditions. We learn from 10 agents and transfer learning to 20 agents right away. As you can see, we can do that with pretty high accuracy. Okay, and because we have two different types, we have a total of 2 squared different interaction laws to learn. So we have this prey-on-prey interaction, which is shown in this upper right left corner, and predator-on-prey interaction, which is shown in the upper right corner. Okay, and this is the prey-on-predator interaction, which is shown in the lower left corner. And then because we have one single predator, there's no predator-on-predator interaction data to learn, so we learn it as 0. Okay, I want to point out that the predator-on-prey and prey-on-predator interaction kernel, these two interaction laws are learned from the same set of data, but we are able to actually learn two different, really different interaction laws, because these two functions are not simply negative of each other. We learn it as two different interactions, because you can look at the scales here. This is 10 to the 2, and this is 10 cubed. Okay, and even the curvature is a little bit different. Okay, so I want to point that out. Okay, and then you can also extend our learning approach to second order dynamics, basically changing the S norm, as I mentioned, as changing the S norm a little bit, and then you can actually fit the learning algorithm to various different things. So in this case, I'm going to show you a second order example of this fish mulling dynamics. Okay, and I also want to show you that we have done a study on the long-term behavior of our estimators. Will the estimated dynamics, the dynamics were produced by the estimated kernels, actually preserve the qualitative self-organized behaviors, in this case, mulling. And in fact, this is a more complicated mulling. This is a double mulling example. That means that half of the fish will swing clockwise, the other half will swing counterclockwise. Let me actually show you a movie on actually how good we are actually preserving this long-term behavior. So initially they are chaotically disorderly placed with random velocity, but we can see that we can actually preserve this double milling behavior towards at large time. Okay, so that's the first one. And then we can also have this is even a more complicated flocking model. This is so-called anticipated flocking, which means that the bird would anticipate the position of their neighboring bird at a future time, just a little bit ahead, anticipating. So with that, you will still have flocking, but then this flocking will be initially around a center of mass direction, axis, and then eventually they will flock at the same direction. Okay, so they will fly around, but because of this anticipation, because they anticipate, they will try to avoid the collision. So you actually have some kind of collision mechanism, avoidance built into this dynamics. And I also want to show you this movie that of these birds slowly, first revolving around the center of mass axis, and then slowly come into flocking together. Okay, so we can actually still preserve this behavior. Okay, so we have that. So we can learn multi-agents, we can learn second order agents. Okay, what if I have my agents constrained on the manifold? That the agents are not freely to move in a Euclidean space. They have to, like for example, for general relativities, they actually constrained to a Lorentz manifold. Can I actually do that? Okay, so then my state belongs to a manifold instead of to a certain Euclidean space. So my original first order system, I need to change that because the pairwise potential depends on Euclidean space between each state. But my state now lives on a manifold. I cannot do that anymore. So I need to replace that by a geodesic distance. Okay. And because of that, I need to know a really nice manifold with the Riemannian magic, because without the Riemannian magic, we will not be able to compute the geodesic distance. Okay. And then we will have to know that, once we know the Riemannian magic, we will be able to compute the geodesic distance. Okay. And then in this case, my phi here is just the pairwise potential, the duality of the pairwise potential taken in this particular form. So this phi is still called the interaction law. Okay. And I'm going to make it at least C1. So I have a continuous first derivative and also compact supported up to the cut locus set of my manifold. Okay, so that is actually defined continuously. And I'm also going to define my directions. So directions this time is going to be a little bit different. It's going to be in the tangent directions from a geodesic from xi to xi prime. If xi prime is not in the colloquial sense of xi. Okay, if it's in the colloquial set, then we don't go. We just set it to 0. So that means that there's no interactions from a points in the colloquial set of its in the colloquial neighbors of this points. Okay, we just cut it down just to make everything continuous. Okay, and because of that, we have a continuous dynamical model to use. Okay, and everything because they live in a manifold, so we need to respect the geometric properties of that manifold. So we're going to design our loss function based on that. We're going to design our loss function based on this tangent space norm of this manifold. And once we do that, then we will still get back the same Euclidean learning rate. Okay, as long as we respect that geometry. Okay, and we'll still have the convergence, in fact, at the same rate of my predicted dynamics converge to the observed dynamics on the same manifold. Okay, so they will not move away. They will just on the same manifold. Okay, and then you probably say, well, what if I don't know the Riemannian magic? Then we will be another research problem to actually look at that. Okay, so here's an example showing you that the same dynamics, a single, not same dynamic, same idea, single predator chasing a group of prey, but now they're constrained on a 2D sphere. So they will not leave the sphere. And because they move in the geodesic distance way, so they only move on the surface of the 2D sphere. And again, the third row shows you the transfer learning case because we learn the interaction law, which is in this time even independent of the manifold, okay, and independent of the number of agents. We will be able to transfer learn that to a system of all agents, even to a different manifold. Okay, so this is because it has 2 types of agents. We have a total of 4 different interaction kernel to it. This is the same setting as the Euclidean space example. Okay, and this is the single predator chasing a group of prey when they are constrained on a Poincare disk. Okay, and then we can still learn, and in fact, this we actually learn better than the 2D sphere case. Okay, because there's more interaction going on with the Poincare disk. So now we can actually learn dynamics constrained on a manifold. We can learn dynamics of agents of different types. We can then learn first order system. We can learn second order systems. But the next thing is, how can I actually put everything into this software package, and then you can actually use it for using the API that we actually develop, and then generate a learning case of your own dynamical system. So let me show you the software package that we have. In fact, if you click on any of this link, it will bring you to this page where we have the package that is finished for our different papers. And then you can click on this particular package for the webinar series, because I cleaned up everything and also updated some of the functions. So this will be the latest package, latest version. Okay, so let me show you how to actually, once you download this code onto your MATLAB, we're also thinking about changing everything from MATLAB to Python later. So, but originally this code is actually implemented in MATLAB, but we are actually slowly moving it away. So if you run the run examples routine, it will ask you to run the examples that we have for each paper. Okay, so we have the PNAS paper, the physical D paper, which talks about the long-term behavior. We have the dynamics on manifold paper, and also we have the second order learning paper that discuss the anticipation dynamics. And then if you just want to run the dynamics, you can just choose the last case. And then we already have all of these different examples building. You can actually go in. Actually, I will show you later. So let's say we'll pick something similar, simpler to run, because the anticipation actually takes a long time. Well, actually, let me just run that. I think it's actually really fast. Okay, so we used MATLAB building the building integrator for MATLAB to actually do that. So actually really fast. Okay, so as you can see, this because the birds anticipate the other neighboring birds at future directions. So they are not flocking right away. They're actually revolving around the center of mass velocity first, and then slowly flock into that directions. Okay, so this is the flocking dynamic example, anticipated flocking dynamic example, and then we can run again. Let's just run the dynamics first. Oh, there's a gravitation example. Let me run the fish milling example. Let's just run the 3. You can also have the 3D example. That's a little bit more complicated. Not sure. Oh, okay, good. So initially they are chaotically. So remember we have this color bar here indicate the flow of time. So initially all of them randomly placed here, but they would just, because of these self-organized forces, and also there's a rally friction force for the environment, they will actually be forced into this milling zone, and then they would just swing all the way around clockwise or counterclockwise all the time. So that's the milling example. And then we have, I also want to show you the synchronization example. So let me run that. That's when you have, should have shown the movie. This is the synchronized firefly dynamics. So when these fireflies, they would actually flock in the spatial space, and also their phases, which is the frequency at which they emit light, would also lock in sync. But because here is only showing the trajectories, if I also show you a movie, they will actually, you can see the lights of them emitting on and off. They will eventually, all of them will eventually flock at the, emit the sync. Oh, actually, let me turn on the movie capability. So let me go here. Make a movie. I think I can make a movie. Yeah. Once I make a movie, I think everything would. Oh yeah, make movie. True. And then let's run this again. 1, 2. Where's the make movie? Well, anyway. Well, yeah. Anyway, so let's go through some of these examples. If you want to build your own dynamical system to use our software package, then you can follow the examples that we have right here. So for example, if I click on this opinion dynamics case, so this file, this opinion dynamics _dev would define the appropriate parameters and also learning parameters for this learning dynamic example. Okay, if you just want to run the dynamical system, then our own building integrator will do first order and also second order dynamics with multiple type of agents, and also with a couple of auxiliary variable describing the emotion or excitation level of your agent. So actually run more than just the example I show in the slides. Okay, so for example, if you want to run an opinion dynamics, okay, and then little d here defines the dimension of your state vector. Okay, you can actually let it go to 10, but visualization purpose, we can only show up to 3. So and then this capital N here is the number of agents in the system. You can choose various different energy-based interaction kernel law. In this case, let me show you the building ones for this opinion dynamics. So they're all complex supported, and then the first one is the one that you have stronger interactions in close range, but weaker interaction in longer range. So you have that. You actually have cluster instead of consensus. Okay, you can change the example here. I can. Oh yeah, this is a continuous case. So we actually have a continuous example building here. You can actually define your own if you want to try other opinion dynamics example. Okay, and then you have to define the order of the system. In this case, is first order, so it's 1. Okay, capital K here indicates the number of classes, the types of each agent, so it's 1 agent. Okay, type info just tells the system that I'm going to send each agent to type 1. Okay, because you only have 1 type. Okay, and then this is the final time to integrate the systems, and this is the initial states that you want the initial configuration for your states vector. That's how you come up with this initial states. Okay, and then this is for the system. Once you have that, you can actually simulate any system you want. The system already have a building integrator and a building visualization to actually show you the dynamics, show you the end results and all the movies. And then after that is the observations, how we actually come up with observations. Okay, we basically just simulate the data. Okay, in this case, how many times, so capital L is how many times we observe in time. Capital M is how many times we observe for different initial conditions. And rho T is actually the initial conditions, the number of initial conditions we use to generate the true distribution for the pairwise data. Okay, and then T naught is the initial time. Mostly we take it as 0. Capital T is the learning time, not the final evolution time of the system. Okay, normally we take it at half. For starting large time behavior, we take it even at 1/10 of your final time. Okay, this is indicate whether you want to also obtain the duality of your observation data. If not, we would just approximate it using certain finite difference schemes. And whether you want to add observation noise to it, you can add noise. We'll allow you to add noise to the observation data and also add noise to the trajectories of the observation data. Okay, derivative of the observation data. So that's for generating the observation data, and then you have the learning, and then you learn it. So you pick a certain type of basis. Okay, in this case is piecewise polynomial, and then there was a subtype. You can use Legendre and all different types. We probably just pick with standard piecewise polynomial, and then that's a degree for the polynomials. And then this one will actually construct the basis for the search space for you based on the system that you have and the observation data and etc. etc. Okay, once you have that, then the code will reading this setting and then assigned, I believe it's here, reading all of these different settings and assign a extra variables for this is the n ratio is for the transfer learning. So whether you want to do a transfer learning case, you can turn this. That means that you want to increase the number of agents to a certain multiplier. In this case, we normally just multiply that by 2. And whether you want to keep the observation data so that you can save the memory and the storage space. And then you can also turn on the parallel capability of this software package. So by default, it will actually run the OpenMP, the Part 4 routine from MATLAB. So it actually run on parallel by default. Okay, and because of that, we're able to handle really large data set or large number of agents too. Okay, and then you can fine tune all of these different parameters, whether you want to keep a lean memory, or you want to have less or more outputs. In this case, this is keeping the parallel capability of these integrators, the learning, and also the integrators. Okay, and at the end, it will actually spits out. So first, it will learn. So let me see. It will learn all of these estimators. Okay, at the end, it will compute the errors between the true estimators, the true interaction kernels and the estimated kernels. And then it will also estimate the trajectory errors, which is the error that we have to actually tell whether our estimated kernel is actually performing well. Okay, for large time behavior, it actually also compute the so-called pattern indicator. So whether we have a mathematical way to tell whether this dynamics at large time is in clustering, flocking, milling, and synchronization. we only have the pattern indicator score for these 4 kinds. Anything beyond that, we still don't know. We still don't have a good pattern indicator score to do that. Okay, but once you know that, we can actually compute to see whether the predicted dynamics is actually in the same desired emergent behavior as the observed data. Okay, we can actually do that, and at the end, you just do a final visualization that outputs the interaction kernels and also all the trajectories data. So let me actually run the whole thing. In fact, let me run the simple one. So run the examples. Let me run the discontinuous opinion dynamics. As you can see, it also asks you whether you want to perform transfer learning. So do a no. Because everything is the initial data is random. So even if you have learned the estimator, the n estimator is actually random, but the true interaction kernel is not. Okay, so the errors is still randomized. So you can actually make it learn, do 10 learning trials, and then you do the same. Okay, so first thing, it will generate the true pairwise distance distribution for the pairwise distance data. Like I said, you will run this way more different dynamics to generate all the trajectories to calculate the true pairwise distance distribution, because this is we don't have a formula, because this is propagated by the dynamics. It's not by any closed form formula. So we actually need to compute that. And then let me go back to there. So let's go back to this. So I have shown you a code demo how to do all of this, how to actually write your own examples to do the dynamics, and also write your own example to do the learning. So you can take all of this code and then try to play with it yourself. It's free, it's open source, it's online on GitHub. So you can do that. So let's go to the conclusion while we wait for that code to run in the background. Okay, so I have shown you on how to do first order and second order forward modeling of self-organized dynamics. We show you some basic examples. Okay, and I have also shown you in actual details how I will actually build up the learning algorithm to learn a first order dynamical system. We learn from a observation of a first order self-organized dynamics. We also extend that to first order dynamics of agents of multiple types. Okay, remember the extension that we did? We basically just changed S norm and everything should follow through. So it's actually really powerful for our learning algorithm. And we also show you how to do a learning of self-organization when the dynamics is actually constrained on Riemannian manifolds. As long as you respect the geometric properties of this data, you will still maintain the same learning rate. Okay, so that's that. Okay. But here's some questions to bring it home, like a homework that you want to do. Is that so for this kind of learning task, because we want to produce a model that is physically meaningful, so we actually need to look at the model to see if that model is actually explaining the thing that actually happening. So for example, this first order model is the change of the state is an average sum of all the interaction kernel weighted by the pairwise differences, right? Okay, so in this case, I'm assuming that my pairwise, my interaction kernel depends only on pairwise distance. But is it true all the time? Why can it depend on just something else or more than pairwise distance? Okay, so we actually extend the idea to say that this interaction law can be as general as possible, depends on just pairwise states, but it's symmetric. That means that phi of xi prime is the same thing of phi of xi prime xi. So we only put a symmetric requirement of this interaction law. Can we still learn that? But then we run into the cursive dimensionality again, because originally we assumed this is only 1D function. Once we extend that, it becomes at least 2D. I mean 2DD, because this each state is a little d vector. So we extend the dimension way a lot. But we have another regression capability to actually do a dimension reduction first and then learn the interaction law. So we have that. And then another thing. So the whole thing is an average sum. There's an average over the total number of agents. So n here. But is that actually practical? Is that actually real? Because for example, for birds, they wouldn't know how to do arithmetic. No birds can do 1/n. So how would they still know? So would there's any topological things that actually building the sensor of these birds so that they can kind of have an idea of averaging, but not actually arithmetic averaging. So we would think that these interactions is actually averaged by the total interactions of the whole systems, okay? Well, for a fixed I. So the birds will feel that. That means that when the density is large, the birds will feel that it's actually a little bit crowded. So the interactions will be a little bit smaller. And then when the density is smaller, is more dense, then you can feel the birds neighboring to you stronger in the sense. So we actually want to build this kind of idea of dense population into this interaction kernel instead of just do arithmetic averaging. Okay, so we're still looking at that. Okay, oh, good. So now it finished. Yeah. So yeah. So go back to the code. So once you've run everything, once you finish the true interaction, the true distribution of the pairwise data, it will learn from only a subset of this dynamical data. It will produce the errors for the it will try to compute the errors between the estimated dynamic in kernel and the true kernel, and then it will also compute the trajectory errors. Okay, and then it will output all of these errors, and also tells you how good this learning matrix is, and then do a final visualization with the comparison of the learned kernel with the true kernel, and also the trajectories. So remember, I didn't do the transfer learning, so it's missing the third row, but if I add it, it will do also another row. I want to also mention that the second row here is a totally new initial conditions. So it's not taken from the initial training data. It's totally new. So just want to focus on the predictability of our estimate. So that's that. So here's all the references, okay, on all the dynamics that we use to generate all the simulated data. And here's the references on how to actually learn from these dynamical systems. I want to point out that we are not the only group that produced the idea of learning from a dynamical system. Cindy is a approach to learn from a sparse structure of the dynamical system. You can also do PIN on this system of ODEs. You can also do new ODEs, etc., etc. But our group is the one that produced the idea that this interaction has a special structure. And we want to exploit that special structure so that we can do transfer learning easier than the other approaches, and also maintain the 1D or even close to 1D learning rate. So, yep, thank you. I think right now is a good time to open for any further questions before I actually close this. Questions? Let me look at chat. No questions? All right.
So I have a question.
Oh, sorry. Yeah.
Given nobody asked a question. So what, I mean, you said it's some special structure and this system can take advantage of that. So can you clarify a little bit more? I mean, this type of structure that other system, that other mechanism cannot capture, or it's captured better or what, faster or what?
So we assume that this systems is not just based on the whole state, it's a pairwise state. So with that, we assume that this right-hand side here is permutation invariant. So that's the first example. That means that if I change any of this order, so if I put xn here instead of x1 and then put x1 here towards the end, this energy will give me the same thing. So that's the permutation invariant that we first assume. If you learn it as just a simple right-hand side of all of these x1 to xn, then it wouldn't tell that if my right-hand side has this permutation invariant. So you actually need to build that into it. For example, if you're using PIN to learn that. So that's the first example. Second example is that this potential also only depends on pairwise distance. So it's only radial based.
Mhm.
It's only a distance based functions. So we also build that in. So once we have the two things, it helps us to maintain the 1D learning rate and also do the transfer learning easier than the other approaches. Yeah.
But then in how general this type of assumption, the structure obviously can probably be used to simulate this flocking and all
Yeah.
of this type of scenario. But how about this permutation invariant and other type of this built-in assumption or structure you're trying to capture? How general?
So far, both basically the flocking, mulling, clustering, synchronization, they can be captured by this permutation invariant and radial-based assumption. But then once you go to swarming, which is more difficult because swarming is like you have the whole dynamic maintains a certain shape, but it's not a fixed shape. It's always changing, but they don't break, right? With that, you can really using just radial based. So that's why we extend the radial based interaction kernel to just permutation invariant. It depends on the state, but it's not just radial. It might be another directions that you can build into there. Yeah.
So also in the beginning, you mentioned the difference between this work and also other type of regression type work because the time is dynamic. So can this thing be also used in that type of scenario when you don't have time built in or something?
If somehow this don't have time building, then you can probably fit some kind of regression to it. But our approach mainly is used for time dependence data. Yeah.
Okay.
So yeah.
Thanks. That's very good. Very top.
Thank you. Any further questions before I close this one down? All right. Thank you so much. Sorry that we actually ended a little bit earlier, but you will have the link to the whole video. And also remember, we have the code, so you can download the whole code package from our website. And then I'll see you guys in our next webinar series. Thank you and have a wonderful afternoon. Bye.